Sorry about that. Had a little bit of technical problems here that messed me up. But we're right back to where we were before. We just found each one of the x values to fill out our table. And now what we want to do is find our y value. Our y values, let's go back to our previous graph to kind of show you what we have here. Remember, we had y sub 0 here, and then we just went up dy and found this new point and used that to write a tangent line for the next one. So these were all the dy's that changed, the calculated dy values that we have in the equation, move us up to start a new linear estimation. So you'll see that these y values are the previous y plus dy. This is going to be the y, previous y of 0 plus the dy of 0.25, which gives us 0.25. Then let's go ahead and calculate our new y prime. It's going to use this x value here. This is 1.25, which can be written as the fraction 5 fourths. 5 fourths is 1.25. That helps us calculate our y prime. Y prime is just the reciprocal of x. 1 over x is the reciprocal. Reciprocal of 5 fourths will give us a value of 4 fifths. That is what y prime is. Now, 4 fifths times dx, y prime times dx, gives us dy. And again, this can also be written as 1/4, not just 0.25, which is going to give us 4 fifths times 1/4. Cancel. You'll see this is going to give us 1/5 or 0.2. Let's go up to our graph now. We've got a little bit of data, and let's just kind of see what has happened here. We started here at 0.10, and then we're going to go dx 0.25 to the right, and then we got a new y value of 0.25. And I know the copies, yours are kind of like mine. For some reason it cut off the zeros here for each one of those 0.25 and 0.75, and of course it neglected to put all the nice negatives in there. But you'll see that we're actually pretty close to our estimate here right off, because when x is 1.25, our new y value here was 0.5. Okay? So we're actually right here. We've got 0.25 is our dx, and our dy was 0.25, so we've actually gotten to that point right there with our estimate. Okay? Let's go ahead and continue on here. This is our new dy value. We know we find y by taking the previous y of 0.25, or let me write it as a fraction. I think that might be a little bit easier for us to see. 0.25 is 1/4. 0.2 is 1/5. We're going to add those together, and that ends up giving us actually, well, I guess the math is easier with the decimals after all. That's going to give us 0.2 plus 0.25, and this gives us 0.45. That is our y value. Y prime, go back to our formula, is the reciprocal of this. 1.5 can be written as 3/2. 1 over x is y prime. And this is going to be the reciprocal of our x value, which is going to give us 2/3, or 0.666 repeating. we have dx times this 2/3 times 1/4 is going to give us 1/6, which is 0.1666 repeating. And that's our new dy value. So let's continue on here and go ahead and calculate our new y value. Y is the previous y, the 0.45, plus the dy value, 0.1666, and that's going to give us 0.6166 repeating. And that's our new y value. Y prime is going to be the reciprocal of this. 1.75 or 1 3/4 can be written as 7/4. The reciprocal of that will give us 4/7. dy is going to be dx times y prime. We're going to take 4/7 times 1/4 and get 1/7, which will give us a crazy number, 1.428, and it's got a bunch of decimals before it starts repeating. We're going to take that value and use that for our new y value. Previous one was 0.6166 repeating, plus this 0.1428 with a bunch of other crazy numbers in there, and it's going to give us 0.758 roughly. Okay. This is the y value that we're looking for. Okay. That is the estimate using Euler's method. Let's go back up here and record that in our diagram. We just kind of started to say, hey, this is where we've gone. So let's plot a couple other points here. At x equals 1.5, according to Euler's method, we'll be up here at 4.5. That doesn't look too bad and too far off of our curve. At x equals 1.75, we predicted or estimated a value of 0.6 something, okay, which is going to put us right about in here, it looks like. And then finally, when x equals 2, it looks like we're just a little bit above 0.75, and you can see that these tangent lines would have all been above the curve and overestimated, but it doesn't look that far off with Euler's method. Again, each one of these points, that was the initial one, and then using the new y value at x equals 1.5 or 1.25, 1.5, 1.75, and 2, we ended up getting an estimate for y sub 2 of 0.758. So how much error did we end up having from this? Well, we know the actual curve is based upon y equals the natural log of x. So y sub 2 would be just the natural log of 2, which is 0.693. Okay. We estimated y sub 2 to be approximately 0.758 using Euler's method. Okay. So our error is going to be the absolute value of 0.758 minus 0.693, which gives us a value of 0.065. So, key is you have to understand what's going on in this. If you need to go back and replay the video to see where we're going, please do that. We're going to do a couple more examples like this, but it's a method of just following the procedure, understanding how you got each value in this, and it will walk you through to that estimate using Euler's method. So let's go back again to that next page where we left off. And in this one, it's asking us to do some more estimates. Again, this is what those formulas were based upon. And now it says, let's do the same thing using a different differential equation. Or y prime is not 1 over x, but now it is y plus 1. So let's go ahead and see how we can do here. Okay? So you'll probably want, you'll need, you can see there's no way that you can fit this on the notes, so you will need a separate sheet of paper, and I've got some graph papers just to help me draw these. So again, we're going to go look at problem number 4, and problem number 4 has some given information. Y prime equals y plus 1. They give us the initial state of x equals 0, y equals 1. That's where we're starting. That's the start. Okay. Then we're looking to estimate y sub 1, which helps us actually helps us find our dx value. Dx, remember, will be the value of x that we're looking to predict at, and subtract the initial one, which is actually pretty simple math here, 0 minus 1. And if you look again on the notes, it said, let's do this in 4 steps. So our dx is going to be 1/4. Same thing we had last time. So let's go ahead and use this to build our table, starting out with our x value. And then in our table, we need a y value, a y prime value, so a column for y prime, a column for dx, and then the dy value that we're going to use to find our next y. Let's start off here. X equals 0. We just calculated dx. Dx is going to be 0.25, or 1/4. And, as a matter of fact, we can even just kind of fill out our x column too while we're at it. We know our next x value will be our initial one plus dx, 0.25, plus another dx, 0.5, plus another dx, 0.75, plus another dx, and that will get us to 1. 1, 2, 3, 4 steps. When we get this y value here, that's where we can stop. And this y value, as we do all those calculations we did before, this is the y value that will estimate y using Euler's method when x equals 1. Okay? So let's go ahead and calculate some values. Well, we don't need to calculate this one. Our first y value was 1, just from what they gave us, 0, 1. Okay. This time, y prime is based upon y plus 1. So we're not going to use x in here this time. We're just going to take this y value and add 1 to it and get 2. dy is y prime times dx. So we're going to go 2 times 0.25 and get 0.5 for our x value. Okay. And then we know that our next y is going to be this y plus this 0.25 that we got, dy, which means our next y value is going to be 1.5. We need that to calculate y prime. We'll add 1 to that and get 0.25 for y prime. 0.25 times 0.2, or 2.5 times 0.25 gives us our next value. Let me write that down so you see it. We're going this 2.5 y prime times dx times 0.25 gives us 0.625. We're going to add that to the 1.25, or excuse me, to the 1.5. So that 0.625. This will give us a new y value of 2.125. We'll add 1 to that and get 3.125 just by using that formula again. Multiply here, and this will give us 0.78125. These two columns always give us dy. Dy plus the previous y value is going to give us 2.9062. Add 1. This will give us 3.9062. Multiply that by 0.25 will give us 0.97656. That value will be added to the last y value that we have, and it will give us our final estimate of 3.8827. Using Euler's method, y at, oops, not 2, but at 1 is approximately, Euler's method is an approximation, not equal to, but it's going to be approximately 3.8827. Okay? So again, the numbers themselves might look very confusing, but the table just builds on the previous line. It all still follows the same process. You've got to understand how the columns are related in order to complete this. If you look in your notes, problem number 5 says use Euler's formula to approximate y sub 1. We're still looking for that. This time using 5 steps with a new differential equation. This one is y prime equals 1 over x squared plus 1. They give us the initial condition at x equals 0, y is going to equal 0. That's our starting point. So we're looking for y at 1. Let's do our calculation for dx. It's still going to be 1 minus 0. 1 minus 0. But this time they ask us to do this in 5 steps. So instead of dx being 0.25, or 1/4, it's going to be 1/5, or 0.2. Let's build the same thing we did before. Let's start out with a column for x. Put all these guys in column x. And then a column for y. And a column for y prime. A column for dx. And then our column for dy. And remember, dy is just these two columns, y prime times dx. All right, so let's put our information in here. We know we're starting at x equals 0. We know that our first y is 0. And if we put in 0 for x in here, this gives us 1 over 1, which gives us a y prime of 1. We've already calculated dx. dx every time is going to be the same, 0.2. This is going to be 1 times 0.2, or 0.2. Our next x value is going to not do 1/4 like we did here, but this time use 0.2. So we'll have 0.2, 0.4, 0.6, 0.8, and then get to 1. 1, 2, 3, 4, 5 steps. Each time adding 0.2. Okay? So remember, we get y from the previous y and dy. 0 plus 0.2 gives us 0.2. I need my calculator here for this one. We're going to put in 0.2, square it, add 1, and then find the reciprocal of that. This ends up giving us 0.9615. dx is still 0.25, and now we're going to take 0.9615 times that 0.2, and this gives us 0.1923. Add that to 0.2. This will give us 0.3923. Put in 0.4 into x squared plus 1, reciprocal of that. And this time we get a y prime value of 0.8630. dx still 0.2. Take that y prime value, 0.8630 times 0.2, and this will give us 0.17241. Add that dy to the previous y, and we'll get 0.5647. 0.6 now goes in here for x squared. When we add 1 to that, find its reciprocal, we get 7582, still 0.25 for dx, and multiply and get 0.7582 times 0.2, we get 0.14705. Add that to our previous y value, we get 0.7117. 0.8 in here for x, square it, add 1, reciprocal. This will give us 0.6092. 0.2. 0.6092 times 2 gives us our final dy value of 0.12190. Add that to 0.7117 and we get 0.8337. So, to answer the first part of this, part A, y at 1 using Euler's method with 5 steps is going to give us approximately 0.8337. Now it says, hey, let's find y double prime of x. How do we do that? Well, we just go back up to this, and we know that y prime is, let's rewrite this. This will be a little bit easier if I just write it to the negative first power. So y double prime will be negative x squared plus 1 inside, subtract 1 from that, times the derivative of the inside, which will be negative, or excuse me, 2x. And that would simplify to negative 2x over the quantity of x plus 1 squared. Okay? And now it says, let's go ahead and find our concavity intervals. Back to what we did in first semester, a little bit of derivatives and then finding concavity here. We know first thing we're going to do is look where y double prime equals 0. We can find that by looking at our numerator. That's when x equals 0. And then also look and see where y prime double prime does not exist. In this case, we look at the denominator, and never going to be an issue here. This is not going to give us 0 at any time, so that is the null set. So we only have the value of x equals 0 when we get a y double prime of 0. And then if we look at this, you'll see on this side, we're always going to be positive. That's when, obviously, the numerator is always going to be positive, but, or excuse me, denominator is always going to be positive, but our numerator, when we're this side of 0 and our x's are negative, are going to give us a positive value for y double prime. But when we're on the other side, when all our x's are positive, we're going to get a negative value, which tells us that this function, this curve, is going to have concavity that is concave down when we are from 0 to infinity for x, and concave up from negative infinity to 0 with open intervals. And now it says, let's think about this. What we just did, are we going to be too high, or are we going to be too low? Okay. Is the approximation in part A too high or too low, and why? Well, let's think about this. We did an approximation when x equals 1. So if we look at what we just did in the previous step, to the left of 0, we are concave up. To the right of 0, we are concave down. 1 is over in this side, over here, which means that we are on the concave down side. Concave down, all of the tangent lines are always above the curve, which means we are definitely going to be too high, since y is concave down at x equals 1. So those are a couple examples that we've done. Let's go back to our notes and continue on with just a couple quick final comments for this. Be careful of your rounding. As you're going through, you saw that I didn't just stop at 2 or 3 decimals. Sometimes I went to 4 or 5. We're going to have to match their answer. So yes, you might say, well, this is the way I did it, but we know these types of problems most likely are going to show up on the multiple choice portion, or we're going to have to match what they have. So carry out those decimals as much as possible to match their answers. And the same thing, use your answer key not as a something to just write an answer in, but to have you to be something that you're going to be working towards. Okay? So, in summary, you can see the steps are all here. The Euler's method. Your initial value of x and y are given to you. Use or find dx. Remember, that's just that x of n minus x of 1, all divided by the number of steps. And that gives you the dx value, which doesn't change, and then build your table. Start with the initial values, and you can see your x's are always the previous x plus this constant value of dx that you have. We evaluate y prime, which in this formula is shown as f prime at whatever x and value and y value. You know that some of these differential equations are going to have x and y determining what the y prime value is. We did one example that was dependent upon y. We did 2 examples that were dependent on x. It could be dependent on both of those, so that's why this nomenclature is in there. We just take that value times the dx. Remember, that was the last column. Add that to the previous y, and that gives us our new value, our new y value. Keep doing that for as many times until we finally get to the last one. That's Euler's method. Okay? Now, to make Euler's method more accurate, we're going to decrease the size of dx, or delta x, or increase the number of steps. So a 5-step is going to be more accurate than a 4-step, than a 3-step. A 6-step would be more accurate than any of those. All right. Hopefully you've been able to get through this okay. I apologize for any technical difficulties. I did run into one a few times, but hopefully this does make sense to you. And enjoy doing homework 14.3.